Good evening. Welcome to the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. And right now, we are on the math part of the videos. And I wanted to mix it up a little bit because in the past, I did more on civil engineering, but this is a STEM channel, which STEM is science, technology, engineering, and math. And on this channel, I'm going to give you wealth and breadth of most of the disciplines that go on or go into STEM. Tonight's going to be no different. Now, last week, I talked about matrix operations. Now, where do we use matrices? For the most part, we can use them in structural engineering. We can use them with eigenvalues and eigenvectors, scalars. We can use them in algorithms. You need your leading one. We can also use them in addition, multiplication, subtraction. So tonight's not going to be any different. In fact, I'm going to talk to you about Cramer's rule. So this video is an introduction to Cramer's rule. Now, Cramer was, for the most part, he was a mathematician. Now let me share my screen here. He was a Swiss mathematician. And he came up with this rule called Cramer's rule. Now, Cramer's rule is a method for solving linear simultaneous equations. It makes use of determinants, and so a knowledge of these is necessary before proceeding. Now, when we deal with Cramer's rule, it relies on determinants. Now we have coefficient matrices as well. Now you find most of these coefficients when we deal with systems of equations. Now, if you are working with a calculator, you can actually put all this information in the calculator and you don't need to utilize Cramer's rule. You can also use Excel, MATLAB. But when you're doing matrices by hand, you can use the coefficient matrix, which is the best matrix to use when you're solving systems of equations. Now, these are systems of linear equations. Now, how do I know it is a linear equation? Because ax plus by equals c. And what's the coefficient? Well, you have your variables x and y, and your coefficient is the letter or numeral that's in front of your x and y variable. Now, you have your linear system, and this is what you call your coefficient matrix, where all of your coefficients are put into a matrix. Now, you have different types of systems. The most common systems, when we deal with systems of equations, it's 2 by 2 and 3 by 3. Yes, you have 4 by 4, 5 by 5. You get more into the Gaussian or Jordan elimination or the row reduction echelon form for those larger type matrices. Now, we are going to talk about right now Cramer's rule for a 2 plus 2 system or 2 by 2 system. In other words, we're dealing with a system of equations, a system of linear equations. So as we move on, we're going to let A be the coefficient matrix. So right now you have your linear system. Your AX plus BY equals E, and your CX plus DY equals F. And we go ahead and make it a coefficient matrix. Basically, you're going to have AD minus BC. Now, if determinant A is not equal to 0, then the system only has exactly one solution. Key points. The denominator consists of the coefficients of variables, x in the first column and y in the second column. The numerator is the same as the denominator. Now, if you understand fractions, your numerator is the top number and your denominator is the lower number. Again, the numerator is the same as the denominator with the constants replacing the coefficients of the variable for which you are solving. All right, example. Let me show you how to apply Cramer's rule on a system of two equations. All right, we have a system of equations. Now, technically, I can go ahead and put it in this calculator. I can solve it, but there's another way to do it as well. We can actually solve it by hand where I can go ahead, I have 8x plus 5y equals 2, 2x plus 4y, or 2x minus 4y equals negative 10. Now, if I really wanted to solve this by hand, one of the first things I would do, let's say if I didn't know anything about matrices and I wanted just to have one variable, well, I would take the bottom equation and multiply it by negative 4. Then I would come up with negative 8x plus 16 equals 40. Why? Because then I would end up with 9y equals 42. That's what you would get. Now I did that in my head. Now 9y equals 42. So then you're going to take and look at the equation. You have 9y equals 42. So how do you get y by itself? Well, you're going to divide both sides by 9. So what you have is 42 divided by 9. Now you're not finished because you can do something with 42 divided by 9. You can divide 42, can reduce it down to 14/3. That's what you can do. But what we're going to do, we're actually going to utilize Cramer's rule. So how do we get Cramer's rule? Remember that formula I told you about, AD minus BC? Well, it's going to work. Now, you're going to get that for the determinant. So how do we get that? Yeah, this is A, B, C, D. So you have A times D gives you negative 32 minus 10 equals minus 42. Now, correction, when I did it in my head, I made a mistake. It was supposed to be negative 42 instead of positive 42. Now, what makes Cramer's rule so beautiful is now we already know what the determinant is. So, for your x and y values, here's what you're going to do. You're going to take and do the same thing. You got your 42. So you're going to have 2 times minus 4 is minus 8 minus a minus 50. Now, when you have a minus and a minus, they cancel out and become a positive. So you get 42. So now you have your numerator is 42 and your denominator, which is your determinant, is negative 42. So that matrix equals 1. Now, something you can also do as a check for yourself when you're utilizing matrices, if you wanted to really find the y value, once you get one variable, you can take the variable that you've gotten, like x, you can substitute it back in the equation and you get your y value. But here, we're going to go ahead and utilize Cramer's rule for both variables. And we're going to do the same thing here. 8 times minus 10 is minus 80. 2 times 2, minus 4, minus 84 over 2. So our solution is -1, comma 2. Those are your points. So that would mean x equals -1, y equals 2. Again, applying Cramer's rule on a system of two equations. Here's how they did it to get your determinant. Now you have your d, and you have your d subscript x and your d subscript y. And this is how they do it. Remember, I told you a times d minus b times c. This is exactly what they're doing. Get 19 here. That's your determinant. That's going to be in your denominator. Your determinant for your x value is going to be in your numerator as well. And you follow the same formula. Same thing with d sub y, your same formula. Now, what I like about Cramer's rule is it can actually, if you follow the formula right, you can eliminate a lot of errors, particularly if you are actually utilizing the system of two equations. Say you don't have a calculator. Well, for the most part, unless you can divide, like if I had a 15 here, well, I could just divide this whole equation by a 3, and then I'll be able to multiply it by -2 to give me one variable. Well, we don't have any of that. And also, with a 2 and a 3, without the matrix, I'd have to multiply by 3 and -2. It's going to give me different values. But with Cramer's rule, you don't have to do any of that. You just turn the system of two equations into a coefficient matrix. Remember, there is a matrix called an augmented matrix, and that's where you include your coefficients and your actual, what you're trying to get. You want to have a coefficient matrix. This is the rule as it applies. Now you can also utilize a 3x3 determinant. Same thing. 3x3 is not bad. When you get into a 4x4 or 5x5, you just have to know how to break everything up, and you got to know your rules too. You got to know your rules. That's the biggest thing. Now, what you're doing is you're actually multiplying your matrices by what we call a coefficient. So you're multiplying, A would be your coefficient, and now you're not using the distributive property, not quite yet. What you're doing is you're basically following the same rule. Like you have 0 times 3, -6, which gives you -6, and then you multiply it by 1. And watch your signage as well. But that's how you start off with a 3x3 determinant. But it's basically applied the same way. Using Cramer's rule to solve a system of 3 equations. This is the formula right here. Same thing as the coefficient matrix. Now you have 3 matrices right here. Coefficient, You have your vector, and here is your third type of matrix. Your non, I call it your non-vector matrix. Here's the formula right here. If D, however, is not equal to 0, then the system has a unique solution, shown below. And here's all the information. You need to get D, and then you need to get D sub 1, D sub 2, and D sub 3. Now let's consider the following equations. This is a system of equations right here. Now, normally for the system of equations, some of us would like to use the Gaussian-Jordan elimination method. I like that method, but that method is very, very time consuming because you have to basically, you have to find your leading ones diagonally, then you have to find zeros here and zeros here. That means you have to utilize the row reduction echelon formula. Very time consuming. You bust out Cramer's rule, it's a lot shorter. And I'm going to get into some calculus later on. I'm going to talk about a rule because of mathematics too. I'm going to go off topic, mathematics. You might look at an improper fraction like 0 over 0. Well, some people say anything over 0 is undefined. Well, I'm going to show you that 0 over 0 equals 1. We use a rule called L'Hopital's rule. That's coming up. So let's get back to the example. So here's our first example right here. All right. You have your equations right here. All of your numbers. Example 1. Now, of course, this is done on a PowerPoint. I didn't do this myself. I'm just giving you an introduction to Cramer's rule. But if you really want to know what's going on, this is the formula right here for 3 systems of equations. And you can go ahead and set up your matrix and then start it. Remember, your denominators for all of your values are the same. And if you really want to see if your equations are working, plug all the numbers back into each equation. Everything should be equal to the value that you want. All right, let's consider the 3 equation system with variables x, y, and z. This is what it looks like. This is for a 3 by 3 matrix. Notice all 3 have the same denominator. Solve the system of equations. Here's how you do it. Now, I could actually, what you would really do to get the numerator, I would actually write outside the probably the last 2 rows, and I'd have a diagonal going this way and a diagonal going this way. And I do the same thing down here. That's how we'll come up with the 23. And these are your solutions. And again, with Cramer's rule, not all systems have a definite solution. If the determinant of the coefficient matrix is 0, a solution cannot be found by using Cramer's rule because of the division by zero. That's why I came up with the zero here. You're going to have to utilize some derivatives, maybe some limits. You're going to have to bust out L'Hopital's rule when you divide something by zero, because it could be infinite. A lot of us have been taught that if we divide anything by zero, it's going to be undefined. Or you can get infinity, you can get negative infinity, you may even get zero, you may even get one. But when a solution cannot be determined, one of the conditions exists. The planes graphed by each solution are parallel and there are no solutions. The three planes share one line, like 3 pages of a book that share the same spine or represent the same plane, which case there are infinite solutions. Again, this is when you get out L'Hopital's rule. So what I'm going to do, let me share my screen again, and let me just give you the overall definition of Cramer's rule for linear algebra. Now, in linear algebra, again, Cramer's rule is a method to solve a system of linear equations by calculating determinants of matrices derived from a coefficient matrix, where the solution for each variable is found by dividing the determinant of a modified matrix, with the consistent terms replacing one column by the determinant of the original coefficient matrix. Only works when the system has a unique solution and the number of equations equals the number of variables. And that's basically it. You're going to find matrices, for the most part, in what we call the infinite series. If you're doing structural engineering, you'll find it in electrical engineering. Matrices are very common, and there are numerous ways you can utilize matrices. Now, on the FE exam, I'm going to tell you this. Use this. You can actually do matrices. Now, the problem on the FE exam, and I will say this, just doing a lot of math here. It's going to be on the FE exam. I will say this, when I took the FE exam before, I never had a 4x4 matrix, never even had a 3x3 matrix. But you can do a 3x3 matrix with your calculator, especially if you're doing a system of equations that has 3 unknowns. You just basically, I'm just giving you the information on how to do it by hand on assignment, but on the FE exam, no, you want to stick it all in the calculator. In fact, if you have a TI 36X Pro, you go ahead and hit, let me get my calculator out for you. One of the equations, you're going to hit what we call system solve, second function system solve. And it's going to give you the equations, and the calculator will do it for you. See, for the FE exam, you have basically 2 to, I'm going to say 3.5 minutes to complete a problem. And when it comes to these matrices, particularly when you use the Gaussian-Jordan elimination system or the row reduction echelon form, it takes so long because you have many, many, many steps. I know I had just completed a matrix. It had 6 pages of paper, and I did it by hand. And you had a number of fractions. Now I just worked on one. If I can find it, let me see if I can do it. It actually, matter of fact, it actually had in In fact, here's an assignment that I have where bottom here, it's a class, bottom here, where you have to do that kind of problem. And what they want you to do is basically you have to set up, when you deal with a system of three equations, you have to set up three matrices. You have to set up the coefficient matrix, the vector of unknowns, and the vector of constants. Now, as this is what I did, here's the equation. Here is the coefficient matrix. Here's the vector of unknowns. And here's my vector of constants. Put them all together, just like that. That's what they're talking about. Now, I actually did that. Now, something else that you need to know if you're gonna do these types of problems, because again, you might not see it on the FE examination. Now, for something like this, I actually did one, and you're given a linear equations. Okay, so what you have to do, you have to take those linear equations and actually make them matrices and then find the points of intersection. Now, I have actually done that. I know it looks backwards to some of you all. I wish I had a board. I would definitely put everything on a board, but I've actually found the determinants and I've actually found the points, but you set everything up in a matrix. Now I set everything up in a 2 by 2 by 2 matrix. That's now for this one, haven't finished this one. I'm going to have to go back and use row reduction echelon form to get the leading ones. But if you really want to challenge yourself, I would say matrices are they're fantastic, fantastic. Matter of fact, I will show you something too. If you really want to see what I did, here's the problem right here. Okay, it's a matrix. This is a system of four equations with four unknowns. Now, if you look at all the work, here's the first page. Here's the second page. This is all one problem now. And you see R1 minus R2, that's row reduction. Here's the third page. It's the work that I've done. I did all this by hand. The fourth page. Now, this is the Gaussian-Jordan elimination or row reduction echelon form. You're going to find a lot. And this is basically if you want to do a matrix with transposing. Well, that's what you do there. That's how you calculate everything, all by hand. This is how you add, subtract all these matrices. If you follow the rules, you can't go wrong. So basically, I just wanted to give you an overview of Cramer's rule tonight by utilizing determinants. And I will talk more about the Gaussian-Jordan rule of elimination too. But in the meantime, just take a moment. You hadn't signed up for linear algebra yet. Sign up for linear algebra. You'll get into eigenvalues, eigenvectors, particularly if you are an electrical engineering student and a mechanical engineering student. Now, mechanical engineering, you're going to use a little bit of electricity. Civil, not so much, unless you're going to use what we call the, they have a series of matrices too, the definite or indefinite. You get into some differential equations if you're going into structural type of engineering, but overall, learn mathematics. And if you need help, watch this channel, and I'll give you examples on how everything is done. And I apologize if they look a little backwards from the camera. The bottom line is I wanted you to see how all these equations are solved by hand. And that concludes this topic on introduction to Cramer's rule for linear algebra. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some political and some social content, you check out my main channel, the 401 Talk Zone Radio Show channel. Now, here's where you find me. You can find me on the 401 Talk Zone Radio Show channel on YouTube, Twitter, which is X, Truth Social, and of course, Rumble. For the QCIS channel, you can find me on YouTube, Twitter, which is X, and of course, LinkedIn. And once again, thank you for viewing and listening to this content on an introduction to Cramer's rule for linear algebra, right here on the QCIS channel. We're on this channel. Get a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. You all have a wonderful and gracious evening.